size effect. So I need to know the dimension, diameter of shaft, and it turns out I go measure it, and it turns out to be 16 mm. So immediately I can calculate the size effect. Okay, size. This is for bending. We are expecting bending, right? So we can just try out for bending, because that's the alternating load is just pure bending. So if I look at the K size for this, it is 0.92. Generally speaking, you won't go much wrong with it. K load, because there is going to be all kinds of torsion, bending, all kinds of things. This is combined load, which means K load is 1. If I do combined load, we'll correct it later, so we don't worry about it. K temperature, it's not a high temperature thing, so we're going to put 1. And so our total SE is going to be equal to let's see, that times 0.74 times 0.92, that's about 306. There, that's the endurance limit. Okay, with that we can now figure out which are the safe and which are the unsafe regions for this whole material. So let me draw this figure and you will see what I mean. So I'm going to draw this figure. This is, by the way, the most important figure. This is what you should really be able to do very quickly. Okay, I'm going to draw this figure. This is alternating stress. This is mean stress. Oh, I'm sorry. Let's do this right. So I'm going to actually shrink it back because I'm drawing it. So this is, I'm going to draw it long. This is sigma mean. This is sigma alternating. Okay. So let's mark some points. Okay. SUT is here. This is 900 megapascals. Look, if your mean stress reaches 900 megapascals, it's going to fail. Right? That's the end of it. That's death. Okay. SE is here. That is 306 megapascals. That's that one. So I'm going to erase this out. I'm going to put it up here. This is 306 megapascals. So I'm going to draw this. This line is called the Goodman line. This is the safe region, infinite life. If your mean stress and alternating stress are anywhere in this triangle, you are safe. If you are outside, it will not have infinite life. Okay, how much life will it have? Let's see. This is SF 765. That's the fatigue strength for 10 to the 3 cycles. If you draw a line from there to here, this one will last anywhere between 10 to the 6 to 10 to the 3 cycles. Okay, and we know how to calculate it. This is the life calculation. So this is finite life. And this is no life. Means it will die within 1000 cycles. Okay, so we want to find out where we are. Are we here? Are we here? Are we here? If we are here, we can figure out how safe we are and so on. Make sense to you? Okay, very good. So now we are going to go to that calculation. So our idea is we need to compute sigma mean and then we have to compute sigma alternating. Okay, so how are we going to do that? Well, we go back to our original figure and we are going to draw some free body diagrams. Okay, so we are going to go back to this figure. So by the way, this dimension was 16 mm okay, and from here to here it's 50 mm. Did I tell you what kind of a beam it is? I told you, to a designer the whole world looks like beams. So this is the wall, okay. Can you see this beam going like that, something like that? Okay, so it's a beam with a disc in the end. No need to panic. As I told you, we are going to draw 3 views: plan view, side view, end view, and then we're going to figure it all out. Okay, so let's go get to that. So our first view, and this is the easy one, end view. And remember what I told you, in the end view we only compute torque, right? So in the end view our figure is going to look like this. This is the disc, and we don't care about the X forces, we only care about Fs. It's 120 newtons. This distance is 100 mm. And remember, this is going to have a torque that goes that way, so there will be a counter torque from the housing T. This is the housing torque. That's the torque. See, that's the torque that you get from your hand, right? When you hold it and you try to do the disc sander, it will try to twist, you know, so you have to prevent it from twisting. That's the torque there, and it has to balance out this one, so it will tell us that T must be equal to 120 times 100, which is 12,000 Newton millimeter. Excellent. And you notice that this is steady torque. This is not alternating, this is mean, steady torque. Okay, so that's as far as the end view goes. Now let's look at the top view. If I look at it from above, can you see it looks like this? The torque, that's one piece. Now we are going to compute the bending moment. So I'm going to look at the top view. And just to make sure, I want to go back and make sure our axis is all sorted out. Can you see x-axis is pointing this way, y-axis is up, and then the z-axis is down. So if I look at it from above, I will see the following things. If I look at it from above, I will see, I'm going to draw this thing like that. That's my wall. Okay. I will see the 200 Newton force like that. And then I'll see the friction force like this. 120 newtons, and this distance is 50 mm. So in the top view I can immediately see a couple of things. One is I have an axial force now. This is force. And then I have bending, which will turn out to be, notice that this bending moment is going like that, and if you remember, my axis was, this is the z direction, that's the x direction, the y direction is actually, let's see, is actually coming out towards me. Like that. So x cross y is z. Okay, so that's the y direction. So this is my equals 120 times 50 millimeters, which turns out to be 12 5 is 60. That's my. Okay, now let's look at the side view. In the side view,